About 15% of the world's population, that is over 1 billion people, experience some form of disability, around 20 million of which experience significant disabilities, preventing them from having a normal daily life. Disability prevalence is even higher for developing countries. In fact, according to the World Bank, there are up to 30 million disabled people in the Middle East and North Africa alone. Today, about 780 million people around the world are suffering, especially from mobility impairment. Mobility impairment is a disability that affects movement, ranging from gross motor skills, such as walking, to fine motor movement involving the manipulation of objects by hand. The wheelchair is one of the most commonly used assistive devices to promote mobility and enhance the quality of life for disabled people. Wheelchairs allow them to have an easier and normal daily life. Thus, the invention of wheelchairs was essential, and they have evolved over the years. From traditional wheelchairs that had to be pushed by a caretaker or require the use of upper body muscles for movement, to electric and smart wheelchairs that are controlled by a joystick mounted on the chair itself. These options are not suitable for all kinds of disabilities, as some people cannot even move their fingers to control the joystick on an electric chair. Also, traction using fingers is not an easy task, especially in the long term. So how about a new control idea? Our project helps people who can't even move their hands and allows them to control the movement of the wheelchair without using a single body muscle. We present BrainWheel, a smart wheelchair that facilitates navigation and performs actions for the users using only their brain signals. We aim to develop a smart wheelchair prototype that is controlled by the electrical signals of the brain and that is capable of taking independent actions to assist the user, such as autonomously detecting and avoiding collisions, moving to locations in autopilot mode, and much more. We achieve this by developing a brain-computer interface system to interpret the brain signals, supported by computer vision modules so that the chair can perceive the environment around it and take the appropriate actions. BrainWheel consists of a brain-computer interface system, or BCI, that enables users to control the movement of a wheelchair by simply gazing at blinking control symbols on an assistive screen. The wheelchair moves on its own based on the analysis of the recorded EEG signals. Additionally, the wheelchair has computer vision capabilities that allow it to take smart actions, such as detecting and avoiding obstacles. It also has an autonomous navigation mode, allowing the user to select a predefined location to which the wheelchair will safely and autonomously go, similar to a self-driving car. The general structure of the project is shown here.
Brain-computer interfaces, or BCIs, measure brain activity, extract features from that activity, and convert those features into a set of predefined outputs. Different techniques are used to measure brain activity for BCIs. We use a non-invasive technique that uses the electrical electroencephalography (EEG) signals detected through electrodes placed on the surface of the skull. We use the generated steady-state visually evoked potential, or SSVEP signals to accurately predict the desired command. SSVEP signals are the brain's natural response when the retina of the eye is excited by visual stimulation at specific frequencies. The brain generates electrical activity at the same frequency as the visual stimulus. Thus, every option the user has is displayed on an assistive screen and blinks at a certain frequency. The user's choice is detected by recording the brain waves, processing them, and passing the extracted features to a machine learning model which predicts the desired action and sends the corresponding control signal to the embedded systems module. Therefore, the architecture of user choice detection consists of the following components. The acquisition, the 14-channel emotive epoch headset is used to record the user's brain activity. Pre-processing and feature extraction, the signal pre-processing is done by applying certain filters to remove undesired frequency bands. then applying a Welch algorithm to estimate spectral density. Classification model. Data now is prepared for the classification process. The machine learning algorithm is used to predict the desired action, which is then sent to the embedded systems module to take the corresponding action. At first, we trained various machine learning models on an online dataset in order to tell which type of models are suitable for our brain signals data and to figure out the most effective data pre-processing techniques. We used the Multimedia Authorizing and Management Using Your Eyes and Mind EEG SSBEP dataset. Its online dataset consists of 14-channel EEG signals data obtained from 11 different subjects performing an SSBEP-based experimental protocol. Data is recorded using 5 different frequencies: 6.66, 7.5, 8.57, 10, and 12 Hz for the visual stimulation, and the Emotive Epoch 14 wireless channels headset for capturing the signals. The stimuli in the experiment were 5 violet boxes simultaneously flickering in the mentioned frequencies. Each box was flickering at a specific frequency, followed by another 5 seconds without flickering. For the signal pre-processing, we first used a common average reference CAR filter to remove any external noise and effects. Then we applied a Butterworth filter to extract the needed frequency ranges. At this point, we used Welch's method to obtain the power at the desired frequencies and their harmonics. An optional stage that consists of principal component analysis (PCA) can then be used to reduce the amount of features provided to the machine learning model. We have trained and compared between 2 machine learning models, Support Vector Machine Model and Random Forest Model, and we achieved the following accuracies. After achieving a suitable accuracy on the models, we started the design and development of the data acquisition process, as well as the development of the GUI to be used for acquiring the brain signals. The GUI has multiple flickering boxes with different frequencies that correspond to the various commands the user may desire. Data recording should be synchronized with the flickering of the boxes. This is achieved by using multi-threaded programming, having main thread for the GUI and another one for signal recording. In parallel, our computer vision module runs a collision detection algorithm and alerts the embedded systems module accordingly. The computer vision module consists mainly of 2 models, an object detection model and a semantic segmentation model, offering a better understanding of the environment around our wheelchair. Starting with the object detection, as shown here, our model classified the objects all around based on predefined categories. Then the semantic segmentation model, as it appears here, divides the area around the chair into specific segments to be able to differentiate between them. We use a stereo camera setup to extract a depth map and occupancy grid of the frontal view of the wheelchair as shown. We attempt to do this from scratch previously with 2 digital cameras and writing all algorithms ourselves. However, this proved to be troublesome. Therefore, we now use the stereolapse camera to facilitate depth map and point cloud extraction, which can then be easily used to create the occupancy grid. This occupancy grid is then used in the motion planning system for short-term decision-making. Our current progress is as follows: occupancy grid creation, distance to collision for every found object, computer vision class with all built-in functionalities, object detection model, and semantic segmentation model. The lowest level layer is the embedded systems module, which is responsible for the project's hardware. It receives its inputs from the machine learning models and directly controls the wheelchair's motorized motion using a TIVA-C launchpad. The TIVA-C driver code consists of 4 abstraction layers. Microcontroller abstraction layer MCAL deals with all the internal peripherals of TIVA-C like SysTick, UART, interrupt, and GPIO ports. Hardware abstraction layer HAL deals with all hardware components interfaced with the TIVA-C like the motor drivers, the GSM module, and the GPS module. Application layer contains the main logic of the system. Auxiliary layer contains standard types and bitmap functions that are used by all other layers. It's also responsible for the GPS module's localization and route estimation for motion planning. We also have the GSM module that is used in case of emergencies, An SOS message containing the chair location is sent to a designated caretaker. Regarding current progress, we have developed and tested the driving code for the microcontroller layer and for the motor drivers. We have also obtained and set up the wheelchair, and we're able to control it through code.
Additionally, BrainWheel supports autonomous navigation and motion planning. The user can choose one of the predefined locations to which the chair will autonomously and safely drive. This is done using the depth map of the frontal view of the wheelchair from the computer vision system. The front image is fed to two pre-trained deep learning models for object detection and semantic segmentation. The output of these models and the depth map are then used to decide the path the wheelchair should take. The path is decided with our custom motion planning system, which is designed to be multi-layer to be able to cope with long-distance planning as well as short-term maneuvers. The motion planning system will have 3 layers. The highest layer is the mission planning, which takes the current location of the user and the final destination and computes the shortest path to take using the shortest path algorithms such as Dijkstra or A-star. The second layer is the behavioral planner, which is a finite state machine that tells the wheelchair what to do in certain situations. The lowest layer is the local planner, which is a short-term planner that uses the outputs of the computer vision module to make decisions in real time. Because our system has multiple parallel tasks, we need those tasks to be done with the least latency possible. We are currently searching for modern techniques to find the best possible solutions. After deciding on the optimal solution for the integration, we will deploy the project into microcontroller boards. We expect that we will use the Jetson Nano developer kit as the heart of the project, and use the TVC microcontroller for motor control. Safety measures for the project. During manual operation, the chair will autonomously detect and avoid collisions with external obstacles. During autonomous operation, the chair will follow algorithms that prioritize the safety of the user. Additionally, in the case of emergencies, an SMS message containing the chair's location is sent to a designated caretaker. Our development process is test-driven. The wheelchair will go through multiple testing stages to ensure the desired functionalities and properties work as expected. Starting from the unit testing of each individual module to ensure its quality and performance, then integration testing to check the system functionality as a whole. Finally, a metamorphic testing phase to review the system from the user's perspective. This helps in eliminating any deployment problems. Here, we show our project timeline for every part of the project. You can find all project subparts and tasks here with their start dates and deadlines. Our project has multiple innovative aspects, including the ability to control a wheelchair without moving a single muscle, sophisticated collision detection and avoidance to ensure safety, self-driving module to ensure maximum comfort, emergency protocols for different kinds of failures, state-of-the-art machine learning models. Our wheelchair is designed and developed with the following core objectives: safety, especially since it transports a particularly vulnerable person; ergonomy, the wheelchair should provide intuitive and efficient navigation with minimum effort; low cost, so it's affordable for people who really need it. This project, if it were to be sold as a fully fledged product, would have a tremendous impact on the industry and the society at large. It would fill a gap in the market for people that suffer from mobility impairment. In conclusion, our project aims to help those people that are in constant need of wheelchairs to move more freely with minimal effort and without external assistance, while at the same time keeping them safe. We hope that this project will make the world a better place for people who are less fortunate than us. Thank you.